Hey friends, it's Ben again. I am recording a video for the Calc 3 class. We're looking at the idea of triple integrals. I'm really trying to make this short, okay? But one of the calculations at the end goes a little bit wild, so bear with me and I'll try to suppress some of the details. So the notion that we're looking at is one that really benefits from a visual. So let me bring up my notes on this. Okay, when I say it benefits from the visual, I wish that I were better at producing the computer graphs because they would be super on this, but instead I'm doing a lot of them by hand. Some things I can kind of computerize, but anyway. So when we talk about our triple integrals, we will write something like this, and you need to know that we refer to it as the triple integral of some function that's given over a region S, and now the region is a three-dimensional sort of object, like a sphere or a cube or something, and then dv. Previously, we had integrals that were dA, and the little elements that we were adding up were going to be area elements. Now we're adding up volume elements like so. This, in my mind, actually makes things a little bit easier to visualize because the big application you can think about is the density of something. You have some sort of an object that is more dense at the core, like a star, and then less dense as you go to the outside edges. And we're thinking about each volume element, you multiply a density times a teeny tiny bit of volume, and you get a bit of mass. And then you're adding things up. Now, definition-wise, what we're thinking about is that the volume element has dimensions xi, y, j, z, k. So the dimensions can all be completely different, okay? And then inside of each one of those volume elements, we are evaluating some function, like density, for instance. And then we're saying, go in there and get all of the possible volume elements that are in our region and add them up. And that is what defines our integral. There's also this notion that you are taking a limit, and I should have written that part down here. So let me push this a little ways over here, and we should have something like this. And this is just a very mathy notation that says the size of the dv's are going towards 0, okay? But then the thing that's most important to y'all to see for this is how we set these up. And the way that we set these up is to simply say that you've got this integral, this inside integral. And I generally am thinking about it as being with respect to the z first, but it could be with respect to any of them. Somebody asked a really good question on Friday about that sort of thing. You can set it up with respect to whichever one of the integrals that you want to on the inside, okay? So here I've set it up with respect to z and said that we're going to have it going from a lower limit, z equals the g on the bottom, up to the z equals the h in the top. And the thing that's going on there is that you think about drawing an arrow upward. And I tried to portray this here that we were drawing upward and then we encountered the surface and then we continued going upward there until we hit the other surface and came out. So your arrow starts at some point down here that's in our region and goes up to hit the surfaces, okay? So that means that once you've got the inside integral actually done, the rest of it is just the double integral that you've done before. The hard part is you're going to have to think about how to get that region there. Generally speaking, you're just going to look for where these two functions that you're thinking about intersect each other. So if they're given to you as z equals some equation, set the two z things equal to each other, and then math it out, algebra it out. So algebra doesn't sound like as cool a verb as math does. So All right, so looking at examples here. So this example just says evaluate, nothing else. And you could totally do that without drawing the picture. But I always try to advocate people looking at pictures here. So I tried to draw what we've got. And this looks like, since it's dz on the inside, the bottom has to be z equals 0, the xy plane, and the top has to be z equals x plus y. And so that's why we have kind of these two surfaces appearing over here. Then the rest of it, the area portion, it says that the y has to go from 0 to x. So that's telling you the upper and lower limits there. And then the x's go between 0 and 2. So that's the reason why that the area we're looking at is this triangle. Okay. Now, as far as evaluating the integral goes, you look in there and you see that e to the x and y, those parts don't have any z's in them. So we'll just multiply by z. The z, 2z here, when you integrate it, you get z squared. And now we have to plug in z equals 0 for the bottom and z equals x plus y for the top. So we do that here, and then there's a little bit of simplifying to do. But the ones where we plugged in z equals 0 are super easy, right? But after I multiply these out and kind of collect things together, then I've got my e to the x sitting outside here, and then I've got to integrate all this with respect to y. So x squared with respect to y, you just get a y. The xy, you'll get an xy squared, and the 2y squared then becomes 2/3 y cubed. And we got to plug in an x everywhere there's a y there, and that gets you this part, and then minus 0 when you plug in the y equals 0. Now you've got a little bit of a mess there, right? But evaluating is still something that we can do. It's just that it's messy. Notice everything there had an x cubed in it, just kind of set up to work out like that. And so then we can collect them together. And when I did that, I got 19/6 for the coefficient. And then I've got to integrate x cubed e to the x. So looking back at what I did here, man, this seems like this was overdoing it. You can get it by integration by parts, or you can just look it up in a table. And if I remember right, the table that I looked it up in just gave the integral of x cubed e to the x in terms of x cubed e to the x and the integral of x squared e to the x, which meant I had to do it again and again and again. So if you are not in need of all the separate pieces and stuff, you could actually accomplish this by going to Wolfram Alpha, or somebody pointed out Symbolab to me the other day. So wow, that one will actually provide you with the intermediate steps. So great. All right, anyway though, so we do all the integration there, and we come down to our 19/3 e squared plus 19. Key to remember, still we don't get variables, we get constants. All of our double integrals always resulted in constants, so do our triple integrals. So, all right, here's another one. And this one, we're going to use a triple integral to find volume. If you're using a triple integral to find volume, that means all you're going to integrate on this is the dv. There's no function to put inside there. The previous example had a function that was inside there, and it was being evaluated at all these points inside of a volume. You weren't finding the volume, you were finding a total of something that varied as the points in the volume. So a little different. But so we need to set this guy up, and our region is bounded by 4x squared plus 4y squared plus z squared equals 16. If you go to something like CalcPlot3D and ask it to draw that for you, I believe that you're going to find out that it's longer in the z direction than it is in either the x or the y directions. Let me think about that and make sure. Yeah, that should be right. So because I kind of like to set things up with a dz first, then I went ahead and solved and said z equals plus or minus the square root of 16 minus 4x squared minus 4y squared. But you can see that a 4 comes out of that, and that's the reason why we get the 2 times the square root there. Okay, So that means our inner integral here will just go dz from negative 2 square roots of blah, blah, blah to plus 2 square roots of blah, blah, blah. Okay? So then you have to do the rest of it. And the rest of it is going to require that you see this equator here where the top and bottom functions equal each other, that's going to be a circle, right? And if you need to figure out how to do it, you set these two things equal to each other, you know, and essentially that means that your 4 minus x squared minus y squared has got to be equal to 0. Or in other words, that you've got this circle here of x squared plus y squared equals 4, which means that you can think of it as y being plus or minus the square root of 4 minus x squared, okay? So then setting up these, we draw our arrow going up, and it enters the region at the negative square root and it exits the region at the positive square root, okay? And then we say how far out do the x's go, and we just look and see that it goes from -2 to 2. So that gets us the integral set up there. Now, the next bit that we do is a little tricky, okay? We have to notice, first of all, our function in here is just a constant. If I wanted to write a 1 there, it might have made it more clear. But that means it is symmetric like nobody's business. We could divide this up into wedges and stuff. As long as we divide them up symmetrically, we're okay. So in particular, I said, to heck with this, I don't want negatives on any of these. I'm just going to deal with the positives and be in the first octant. Octant means divided into 8. So then I had to put an 8 out front. So that makes this look a little bit neater as we're going along there. But we integrate the dz, no problem. And you're just going to plug in the bottom and the top. And that's the reason why you end up with 2 times that square root. Then we have to integrate that with respect to y. Now, I went and looked up a formula for that. And since we were integrating with respect to y, then y is my variable. I kind of treat it like a u in the formula. And then I treat the rest of it as a constant, and I make that be the a squared in the formula. I think, yeah, here's the formula here on the next page. Okay. So, so that's there. I'm trying to integrate, and I have to recognize how to look it up into a table. So once I do that, then just interpreting here, the y is the u, and the 6 minus x squared, the square root of 6 minus x squared is the a, okay? And so that means that we end up with the 4 minus x squared minus y squared for this bit. And we have a 4 minus x squared for the a squared, and arc sine of the u over a looks pretty nasty. But when we plug it back in, or when we plug in that square root there, we're going to be taking an arc sine of 1. That's actually super nice, okay? All right, so anyway, plugging in the upper limit and then the lower limit, when you plug in the upper limit for y squared, that means that the 4 minus x squared minus y squared, you're going to end up having to subtract something from itself, and then that's going to turn into just 0. And then this bit here, oh, I used the wrong color. Hang on. This bit here turns into a 1. The arc sine of 1 is pi over 2. And then nicely enough, all this stuff over here had a factor of 0 appearing in it, or I'm sorry, a factor of y appearing in it. So when we plug in the y equals 0, all this stuff just vanishes, okay? So, oh, and so is this bit. So that means that we end up with the 4 minus x squared, arc sine of 1, so the pi over 2 in that part. And so you can combine the 8 and the over 2 to make things a little bit nicer here. But you have to integrate, it's just a polynomial. And then you just plug in, and your arithmetic tells you that you've got 64 pi over 3. If you said, hey, look, guys, it's an ellipsoid, and I know that the volume of an ellipsoid is given by the formula 4/3 pi ABC, great. But the point was to actually get an example where we had to set up the integration. All right. Okay, so this next one here asks us to integrate this sine of y squared dz. So when we integrate sine of y squared dz, no problem, there's no z, so it means you just multiply by a z and then go from the bottom limit of integration to the top. So you really end up with just 3 minus 1 or 2 times this sine of y squared dy. But that gives us a sad face, okay? Because that's something that it is integrable, but it does not integrate to a function you know the name of, okay? It has a dumb name like the sine integral function or something like that. It's a special function. It exists. It's just not formulas that you're used to, okay? It's not an elementary function. All elementary function means is functions you know the names of, okay? All right, so then the trick that we're going to use is to reverse the order of integration here. And so we draw out the picture that we can tell from the limits of integration that we're going to be going from x to a constant. So that means that we'll have limits that look like that. And then we check, and our x values that we cut off at make it into a triangle. So we draw that region out, and then we look at the region and try integrating the other way. And when we do that, now we have our limits of integration being 0 to y, and then our y values going from 0 to root pi over 2. So that we can integrate with respect to x, and we pick up and have now a 2y sine of y squared, and that's just ripe for a u substitution. Plug in, you have minus cosine of y squared, and from there it's arithmetic and it comes down to just 1, okay? So one of those things that we keep emphasizing because of the fact that fact that those are tricky problems, okay? So this one did not tell you to reverse the order of integration. You had to figure it out on your own. So, okay, so this one asks us to set up an integral across a region Q that's bounded by this here, and that there. Somebody made the observation the other day, hey, if it has things set up in, you know, exactly that way, doesn't that just tell you what to do for the inside limit of integration? Yeah, it does. And then for the outside limit of integration, and then for the outermost. So with regard to this, the volume we're thinking of has as its base this little parallelogram here. And I tried to draw that as best as I could there. I did not attempt to produce then the piece that's going to be here in the background, okay? It looks a little bit like a soccer goal, I guess. But that's what we're talking about setting up the integral over. Notice though, with the f of x, y, z, we're setting it up. We're not actually evaluating it, okay? So we can see that our bottom limit of integration for the z needs to be 0, and the top needs to be this 1 minus y squared. So we do that, okay? I would always advise set them up from the inside out, okay? Then once we've got that, we have to look at that region on the plane here. And because of the fact that it is simple in the horizontal direction, but not the vertical direction, I went ahead and integrated dx first and then dy. So integrating dx first, you draw your arrow across and you're hitting each of those curves in turn. And then you have to say, how far up and down does my y go? And it just goes 0 to 1. So we just have those cutoffs there, and then we get it done. Sometimes the question just asks you to set up, doesn't ask you to do everything about it. By the way, one question I've had from a couple of people is, oh my God, I can't draw these 3D things. Well, it's okay. You don't have to do a super good job with it. If you can get a picture of it from graphing software that's good enough for you, that's good enough. Okay. When you're doing homeworks and have to do that, then you may need to copy and paste from one thing to another. Also had an observation from somebody, hey, that's a huge pain in the butt. If I can see it on the screen and then draw a picture of it on my paper, is that going to be good enough? Yes, it is. Okay. You don't have to produce something electronically unless you just want to. Okay. If you can produce it by hand without ever going to the software, great. But if you need to see it on the screen and then you want to trace it on the software or trace it on the paper, I will try not to grade on your art ability. Okay. If your art's really bad, it might hold you back, but I'm trying not to let that be the case. So, all right. So this one here is asking us to integrate 1 plus z. I chose something there that was just not a constant because of the fact that I wanted to illustrate that the things that we're doing with triple integrals doesn't have to give you a volume. If you got a function other than just one, it's something other than volume. Maybe it's mass, maybe it's like a total potential energy or something. I'm not the applications guy, so I should just shut up. But so the thing we wanted is a sphere, x squared plus y squared plus z squared equals 6, and a paraboloid, z equals x squared plus y squared. So I tried to draw those electronically and I could not get a picture that I thought was good enough for y'all. So I went ahead and drew it just by hand. So we know that the bottom is supposed to be this paraboloid shape and the top is just a piece of the sphere here. So I just drew that bit. So with getting this figured out, we're going to have to think about where these two things intersect. And the trick on this is that you have x squared plus y squared appearing here and here. So instead of trying to do something where you're solving for z in both of them, just substitute z in for the x squared plus y squared. Then when you do that, it factors nicely. Your z has to be either -3 or +2. Because of the picture we have being above the xy plane, we know it's +2. And that means that the region of integration, when you look at the shadow down onto the xy plane, that you would have, coming down here like so, that shadow then is going to have boundaries x squared plus y squared equals 2, which is not the same as the boundary that you would have by looking all the way out to the equator of the sphere, which makes sense because we only want the part that is above the paraboloid and below the sphere. So, all right. Anyway, though, so you're going to be integrating 1 plus z with respect to z, and it goes from the bottom to the top. Okay. Now, we will pay the price for my putting in that 1 plus z as we go along here. So with the setup, once you know that you've got this circle, x squared plus y squared equals 2, then we can set up our integration here, and we can say to ourselves, okay, as we draw an arrow up, we will hit the minus square root and the plus square root as we enter and exit the region. So that's those. And then we have to say, where do our x's go to? And they go to the minus root 2 and the plus root 2. Okay. So we have it set up, and this 1 plus z in here doesn't have super duper symmetries. Okay. So we might be okay doing something right away, but it's not super obvious that we can. So we will do the integration with respect to z, and you just get z plus 1/2 z squared. And then when you do that, you're going to have to plug in and get this square root, which will work nicely with the c squared, but not so nice with the thing that's not squared. And by the way, I'm noticing that I just kind of left a stray dx dy hanging on there. That was weird. Okay, so then you're going to plug those in, and you plug in the square root to both places, and then minus, and then you plug in the x squared plus y squared to both places. Now, this we can't do anything with, but everything else here we can simplify. It's just polynomials, but it's a lot of polynomials. So square roots here, and then you end up with all that. Notice, however, that x, everywhere that it appears, has an even power. Y, everywhere that it appears, has an even power. That means that we have even symmetry. And so I think the next step here, the next step is we will multiply by 4, because we're talking about stuff in the xy plane, not the xyz space. So we just have quadrants, but 4 times, and we'll have our limits of integration be 0 to whatever. That doesn't really accomplish all that much. It just means that we have to write less crap. So, all right, so now we need to integrate all of this. And as I mentioned, a lot of it's a polynomial. That's not going to be too bad. This part, not so great, you know? So we have to know what the integral of this is, and we did that on a previous problem, fortunately enough. And let me see here on the next page. Please bear with me. I wrote down all of the various formulas we need, but that was one of the formulas. And I plug in here, and so I have all this stuff, and that's the integral of just the first piece. And then all the rest of it was an integral of the polynomials, and I had to plug in y equals the square root, and then plug in the y equals 0. Now the nice thing is when you plug in the y equals 0, everything goes away, because everything has a factor of either y or something like y. Okay. So you plug all this stuff in, like we had on a previous problem. We end up with a 0 here in one spot. We end up with an arc sine of 1, so we end up with a pi over 2 in another spot. But then all the rest of it is messy, messy, messy polynomials, because of the fact that we end up having odd powers of a square root. Okay. But since we have a factor of a square root for all of it, I went ahead and just factored it out. And I did not make you sit and watch all the algebra to get this done here. I hope I did the arithmetic of it right. But once we've got that, then we're trying to integrate this stuff with respect to just x. And it's super messy, but we can do super messy. The thing is, you've got a constant times a square root, an x times a square root, an x squared times a square root, and x to the 4th times a square root. So that means that we're going to have to know an integral of just a constant times a square root, or x times a square root, or x squared, or x cubed. That one there, by the way, is not in the standard tables, and I actually went to Symbolab and asked it to do that for me. So, and they don't simplify everything nicely. So I still had to do a little more simplifying. Anyway, though, so once you've got all that stuff as your integrals here, we're going to have to plug in the square root of 2 and the 0. Plugging in the 0, by the way, everything's got a factor of x or arc sine x. So that's going to be good, all right? But plugging in with the square root of 2, oh my. All right, so here's all the integral stuff. And then here's stuff with the square root of 2 in there. Now, one thing that occurred over and over again was that we had an arc sine of the square root of 2 over the square root of 6, which is arc sine of 1 over the square root of 3. And if you're thinking, aha, special angle, nope. Arctangent of 1 over the square root of 3 would be a special angle. Arcsine of 1 over the square root of 3 is just some damned angle, you know? So anyway, you get lots and lots and lots of stuff there, and a lot of it has factors of square root of 2, and some of it doesn't. So we actually get something that's an integer, believe it or not. But then this is a horrifying mess, and this is another horrifying mess, and this is something with a non-special angle in it. So obvious question that you're thinking is, do I have to do that? Are we going to encounter that a lot? No. You may have problems that take quite a while to work out, but that one there was just, I made something up off the top of my head and it went awry. So, but I feel as though I ought to go ahead and just finish those problems out, not make you finish them out, but I should finish them out because, you know, it can be done, so it should be done. So anyway, this gives you some ideas about setting up triple integrals. It's really setting up an inside integral and then doing a double integral that you already did some of. Okay, so go ahead and see what you can do on the homework on that. I will see you all later.